İşlemciler Laboratuvar dersine hoş geldiniz. Abbas hocam, Ammar Abbas yazıyor. Öyle ben onu bilmiyordum. Abbas hocam dersi anlatmaya çalışacak. Ben de gerektiği yerde katkı yapabilirim. Buyurun hocam.
Hocam ilk adım var benim kullanmıyorum ama Yanmar diye bir adım var maalesef.
Evet,
Ee,
güzel
evet,
isim.
teşekkür ederim hocam, sağ olun. Evet arkadaşlar, bu haftaki konumuz compare ve jump'lar. Öncesinde şöyle bir Türkçe neylerden bahsedeceğim. Kayıt sırasında sonrasında dersimiz İngilizce olacak. Ders bittikten sonra anlamayan, sıkıntı yaşayanlar için bir Türkçe özet gibi bir şey daha geçebilirim sizin durumunuza göre. Bilginiz olsun. Bu derste işleyeceğimiz bilgiler biraz ağır. Yani çok fazla bilgi arka arkaya gelmiş gibi olacak. O yüzden kaçırmamaya çalışın. Kaçırdıysanız da lütfen bu dersi tekrar izleyin. Çünkü bu ders gerçekten en önemli derslerden bir tanesi. Bu compare bizim if, else yapma kabiliyetimizi arttıran komut, instruction, compare komutu çok önemli. Onun dışında jump'lar, emülatörü açtığımız zaman, help'i açtığımız zaman instruction set'te burada çok fazla komut var demiştim, hatırlarsanız. Bunların hepsini işleyeceğiz demiştim. Bunların yarısı neredeyse jump. Bakın JA, JAB, JB şeklinde bunların hepsi jump. Ama kendi condition'ları var. Yani durumları var. Mesela JA jump above demek. Büyükse atla. Jump above or equal. Büyük ya da eşitse atla. Pardon arkadaşlar. Jump below. Küçükse atla. Küçük ya da eşitse atla. Carry flag set edildiyse atla. Eşitse atla. Büyükse atla. Büyük ya da eşitse atla. JL neymiş mesela? Less than, lower than, less than atla. Çeşitli condition'lar var. Bir tane jump. JMP. Bu jump condition'ı olmayan, direkt atlayan jump. Bunu bilmeniz gerekiyor. Bunların hepsini ezbere bilmenize gerek yok. Bu kısmı Türkçe açıklamak istiyorum. Bu jump'ların her birini ezbere bilmenize gerek yok. Fakat bazı durumlar için bazı jump'ları kullanıyoruz. Kendinize jump seçin. Mesela JZ zero flag set edildiyse atla demek. Çok kullanılan bir şey. Ya da JE eşitse atla. Bu ikisi birbirinin aynısı. Bunlardan birini seçersiniz. Ya da küçükse atla, jump below ya da jump lower. Bunlar da birbirinin aynısı. Kendinize göre jump seçip o jump'ın hangi durumda atladığını bilmeniz gerekiyor. Bu derste anlayacaksınız hangi durumda atladığını bilmeniz ne demek. Ondan bahsedeceğim. Onun dışında şöyle bir tutorial'ımız var. Tutorial for Beginners diye ana indekste tutorial'a girdiğiniz zaman Program Flow'un altında. Program Flow. Program Flow jump'ları anlatıyor. Unconditional jump dediğimiz o tek jump, hiçbir şarta bağımsız olarak atlayan jump ve diğerleri şeklinde. Diğerlerinden kastımız da hani dedim ya, mesela jump above'la jump greater ikisi aynı şey. Büyükse ya da büyükse atla, üstünde ya da büyükse atla. Aslında onlar birebir aynı şeyler değiller. Farklarını tablolaştırmışlar. Bu tutorial'ın program flow'un altındaki tutorial'da farkları tablolaştırılmış. Mesela bu tablo, farkı olan tablo değil de bu işe yarar bir tablo. Tek bir bayrağa bakan tablo. Tek bir bayrağa bakan tablolar, jump'lar. İşinize yarar. Birbirinin aynısı olan, aynı bayrağa bakan komutları yan yana yazmışlar. Bunların opposite'leri, tam terslerini de yazmışlar. Mesela jump below, jump not below, bunlar birbirinin tersi. Jump greater değil, tamam. Diğer tablolar. Jump'ların birbirinden ayıran bir diğer özellik de signed ya da unsigned number'lara göre tablo oluşturulması. Mesela bazı jump'lar sadece signed number'larla çalışıyor. Yani işaretli sayılar dediğimiz sayılarla çalışıyorlar. Bazı jump'larsa unsigned number'larla çalışıyorlar. Buna dikkat etmeniz gerekiyor. Mesela JA ile JG aynı şey gibi geliyor. İkisi de jump if above demek aslında. Ama JA unsigned number'larla çalışıyor. JG signed number'larla çalışıyor. Farkı bu. Böyle iki ayrı tablo var. Bunu bilmeniz gerekiyor. Yani kendinize jump seçerken hangi tablodan ne amaçla seçtiğinizi bilmeniz gerekiyor. Bunu size bırakıyorum. İstediğiniz jump'ı kullanabilirsiniz. Zaten sınavlar sırasında emülatör de açık olacak. Tarayıcınız da açık olacak. Kullanırsınız. Evet, bundan hızlıca bahsetmiş oldum. Aklınızda da bir şeyler canlanmış olsun. Şimdi müsaadenizle İngilizceye geçiyorum. Şöyle bir girenlere de bakayım. 11 kişi olmuşuz. Tamam. Derse girmeye çalışın arkadaşlar. Bu ders dediğim gibi biraz ağır bir ders. Bu arada benim kameram dondu. Niye dondu? Oh. Neyse ben kameramı kapatıyorum o zaman. Kameram yine dondu. Okay. Today's topics is compare and jumps, and we are going to cover the lab 3 assignment. Lab assignment 3. We have 3 examples we are going to solve, and mostly we are going to talk about the jumps and their conditions. We are going to cover the flags. These flags are important for us in order to use jump. For example, GE, jump equal. I'm going over and looking at the instruction set and go over to jump equal. Jump equal is only looking for the zero flag. If zero flag is set, then jump equal will jump. Okay. Let's go and look at another flag. Jump not lower. For example, jump not lower. Short jump if first operand is not less than second operand. Algorithm if sign flag and overflow flags are same. If sign flag and overflow flags are same, then this jump jumps. Okay, every jump has condition in it. For example, jump greater, looking at the sign flag and overflow flag, and they should be equal. And also zero flag should be 0. So jump greater is not a easy jump. JA, jump above, is less complicated one. A carry flag should be 0 and zero flag should be 0 in order to jump. Okay, these are jumps. And compare. Let's go over and look at the compare. Compare operand is important. It takes 2 parameters. It can be register memory combination, memory register, or it can be register, memory immediate, register immediate. But there is no immediate memory. There is a catch. There is no immediate register. Okay, be careful. Parameters are here. We compare. How do you compare two numbers? We compare the numbers by subtracting. Let me try to open my cam again. There's something wrong with Wi-Fi, I think. Anyway. Okay, we compare the numbers, the values, by using subtract operation. But the important part of this compare instruction is result. Result is not stored anywhere. This subtraction is done. The flags are set according to this operation, but the result is not stored anywhere. I'm going to write some simple codes like add AX to subtract AX7, increment AL. That's it. Oops, we put necessary comma. Okay, remember we have flex button at the bottom of this emulator. Open the flags. Flags are very important. We should know what those flags are meaning, what those meanings of these flags are. Carry flag. Carry flag shows the carry between instructions. For example, if you add two elements and the result will be more than, for example, 8-bit, carry flag will be set. Another example will be, for example, make a subtract operation, which result is minus. For example, 3 minus 5. 3 minus 5 generally needs a borrow flag, but we don't have a borrow flag. Carry flag also shows us the borrow flag. So this is carry flag. By the way, all of the flags can be found. Where can we found the flags? Let me go over the tutorials. Variables, not variables, arrays, constants. Oh, this is not memory access, variable, interrupts. Flags. Yeah, flags actually a 16-bit, a single register. One of those registers bits are used as a flag. For example, overflow flag is the 15, 14, 13, 12, 11th bit of this arithmetic logic unit register. Where are those flags? I can't find them. This is not interrupt, not these ones. Arithmetic logic instruction. Okay, flags. It's under tutorial part 6, arithmetic logic instructions. Flags. As I said, this is a 16-bit register, a single register. We can't use directly those registers. Let's go over and look at the flags one by one. Carry flag. This flag is set to 1 when there is an unsigned overflow. For example, when you add bytes 255 plus 1, result is not in range between 0 and 255, so it's set to carry flag to 1. If there is no overflow, flag is set to 0. 0 flag set to 1 when result is 0. For non-zero result, this flag is set to 0. By the way, if you open this flag instruction and put mouse over this flags, a pop-up, balloon pop-up will show you the meanings. For example, 0 mean not 0, 1 mean 0. Sign flag, 0 mean positive, 1 mean negative. Overflow flag, parity flag, auxiliary flag, interrupt enable flag, direction flag. These are all explained in here. Sign flag is if there is 1, it means the result is negative. When the result is positive, it is 0. Actually, this flag takes the value of the most significant bit. Remember, if the most significant bit in signed number is 1, it means it is negative. Overflow flag set to 1 when there is signed overflow. For example, when you add bytes 150, result is not within the range of this minus 128 plus 127. So this is set to overflow flag. Parity flag, this flag is set to 1 when there is even number of 1 bits in result, and to 0 when there is odd number of bits. Let me explain this a little bit further. For example, we have a number, I don't know what number, 4-bit of this number is this, and this is another 4-bit. This is 8-bit number, and let's say this is in the result. We make subtract operation or add operation, and this is the result for now. Emulator look at the value, count the ones. There are how many ones? 1, 2, 3, 4, 5 ones. 5 means odd. Odd means, let's go over and look at the parity flag. Odd means 0. So parity flag should be updated with 0 if the result is this. You should count the number of ones in the result. Okay, parity flag is dead. Auxiliary flag set to 1 when there is unsigned overflow for low nibble bits. Okay, nibble means 4-bit. Let me open this again. For example, AH, AL. This is AX. Remember, we have a number, let's say 2B, 1E, H value in here. Every 4-bit is called nibble. Word is nibble. As you can see in here, every 4-bit is called nibble. This is nibble and this is nibble. If there is an carry and borrow between these nibbles, which is also can be called overflow, this auxiliary flag set to 1. Okay, it can also be in higher boundary operation. So the result, if the result is AX, it looks for every nibble. If the result is AL or AH, it looks for only single nibble. Okay, auxiliary flag is this. I know these are boring things, but you will use these flags in theory and lab always. Interrupt enable flag. Interrupt enable flag means these programs now accepting interrupts. If this is set to 0, which means this program cannot accept interrupts for now, because it's called a function and it's running that function. You can't interrupt again. That is for that usage. It means that it is now in the subroutine or an interrupt already. You can't call another interrupt. You have to wait. That is that for. Okay. Direction flag. Direction flag is, remember, we have also stack in here. We goes like here from top to bottom. When we change the direction flag, we goes from bottom to top. The direction is called will be used in the stacks, updating index. Okay, these are the flags and or operation, etc. Let's close this one and look at the flags in here. Instruction by instruction. For example, move AX2. We put 2 in AX. Let's look at the flags. There is no flags change. No need to. Add AX2. There is no flags change. Okay. Subtract AX7. But there is lots of flags is changed. AX is 4. This operation is doing 4 minus 7. 4 minus 7 is minus 3. After this operation is done, look at the sign flag. Sign flag saying that the result, which is AX for now, is negative. We know that in here. You can see FFFD. The result is negative. The result is not 0. It is this is showing that. Carry flag. Carry flag is set to 1, but this time this is actually borrow flag. Borrow and carry is shown in the carry flag. Okay, let's increment AL. Look at the auxiliary flag. Auxiliary flag count the number of ones in FFFD. For example, FFFD has some number of ones in it. It's saying that how many number of ones? Odd number of ones. Oh, parity flag doesn't change. Auxiliary flag. Auxiliary flag is changing because auxiliary flag was, what was that? Let me open the part again. Set to 1 when there is unsigned overflow for low nibble. Within the low nibble, within this AL, there is unsigned overflow. When you increment this 1101 by 1, it becomes FE. FE change the lower to higher 1 bit, so that auxiliary flag set to 1. No, actually it's set to 0. It was 1, set to 0. Anyway, we use some, let's say we put 7 in AL, subtract AL7. Simple, meaningless code. We put 7 in AL and subtract 7 from it. Let's open the flex, by the way. 7 minus 7 is 0. As you can see, 0 flag becomes 1. Because the result is 0. Okay, now I'm going to use not sub but compare. Compare AL with 7 and open flex again. AL is 7. Compare operation. Compare operation is, remember, subtracting first operand from second operand from first operand, meaning AL minus 7. AL minus 7 is currently 0, so the 0 flag becomes 1. Okay, compare operation makes subtracts, but look at the registers in here. I'm going back and forth. There is only one change, which is instruction pointer, which is always changing. So the result is not stored anywhere. That's important. Compare is not changing anything at all. It just updates the flex according to this instruction, which is subtract operation. Okay, we cover this compare. There are compare parameters. I'm not going to cover all of these. Register. For example, AL, which is always 0. AL, CL, or AX, CX, AX, CL. These are all register combinations. But there is no immediate memory or immediate register. Be careful, register immediate, which is we have used already. This is register immediate. Okay. Now I'm going over to jumps, starting with unconditional jump. From previous week, remember, this was loop, and we know that these loops runs CX times. For example, in here, it will run 5 times. This will run 5 times. And let's count this in the AL and see this run 5 times. Look at the AL is already 5, the program is finished. Okay. So now I'm going to update this loop with unconditional jump. Unconditional jump takes one parameter. This is just a label or 4-byte address. Just never mind this 4-byte address for now, because we can't directly calculate the address and execute commands. For now, know that we only use label, a single parameter which is label, and it jumps to that location. For example, increment AL again. This is not important anymore. When I run this code, for example, with a small delay, please look at the AL. AL is increasing. Instruction pointer is keep updating with 024, 024, 024. But it goes like this. This is endless loop because this jump has no conditional case to stop at some point. Yeah. So I'm going to decrease the delay, and the result, as you can see, is endless loop. So jump is unconditional. For example, we have a program like increment AX, move 1000H, some value. Between there's a labels. After this label, there are some codes again. And after that, I said that jump to that location. It just directly jumps to that location. But this can also be vice versa. For example, like this. For example, I write some codes in here, and I don't want these codes to be run. And let's emulate this code and see the result. For example, we put some 7 in CX, increment AX. Now, jump condition, unconditional jump. It directly jumps into this label, and which will finish the program. The program is finished. The between code never run. So this is unconditional jump. Let's write some conditional jump. For example, jump equal. I'm going to put some value in AL like 5. I'm going to decrease AL. That's it. Let's say this is a block of a loop. We put 5 within this operation. I decrease AL and no. Add some value to CX like 1 and decrease AL. Decrease operation. I'm going over and look at the decrease function. Decrease function can change the zero flag. This is important. Decrease function can change the zero flag so that GE, jump equal, which is looking zero flag, can jump. But now I'm going to opposite. I'm going to use the opposite version of jump equal, which is jump not equal. Let's go over and look at the jump not equal. Jump not equal means zero flag is 0, then jump. If zero flag is 0, then jump. If it is 1, it will not jump. So let's emulate this code. Okay, we put 5 in AL. CX increase, add 1 to CX. CX is 1. Decrease AL. Decrease AL will update the flags. All of these add, decrease, move, all of this function change the flags. But the last function, which is decrease, is important. We are going to look at the change of what decrease function does. Okay, look at the flags. There is no flag change. And we jump. Why we jump? Because GNE says that if zero flag is 0, which is the case now, zero flag is 0, it jumps. Okay, AL is 4. Now AL is 3, AL is 2, AL is 1, and now AL becomes 0. As you can see, 0 flex becomes 1. I'm stepping back and forth, back, forth, back, forth. As you can see, decrease comment, decrease the AL into 0. 0 is the result. Result becomes 0, so 0 flag is set to 1. 0 flag is set to 1 when the result is 0. Okay. Because the result is 0, this will not jump and the program is finished. So the CX becomes 5. This loop is run 5 times. Because we put 5 in AL. Let's put some value, for example, 10 digit, which is A. And this will run 10 times. Look at the AL 210. If you look at the CX, which is the total number of runs, because we keep adding 1 to CX, it is 10 times. So this is conditional jump. We make a loop according to some conditions. For example, if I did not put anything into AL and emulate this code, it will run until AL overflow to 0. So this will be very time consuming because it is going 8, 9, 8. Actually, we are only using AL and AL becomes 0, overflowed and finished. So you have to be careful using conditional jumps. It may not be as expected. Okay, these are conditional jumps. We can use the compare JJJ. Yep. Let's go over to examples. Is there any question, by the way? There are some questions. Yes, we can. The first question is actually that. Let me cover your question with example 1. Example 1 is a simple if-else statement. Why I can't open that? Example 1. Write a program that analyzes 1000H memory address. If value of this memory address is equal to C2, write FF into 1100H address. If the value is not equal to C2, then write AA. So actually the program is if 1000H address is equal to C2H, write what? FF where 1100H as right AAH, right? Yeah. Question want us to check this location of this memory if it is C2 or not. If it is C2, write FF into another location. If it is not C2, else write AA into another location. Okay? This is the program we need to write. Let's put commas because this is not C. Okay, so what? Let's put some value into 1000H so that we can check if it is C2 or not. Let's put AB hash into 1000H address. Now I'm going to check if this memory location is, I need an if, but there is no if. That's why I'm going to use compare. I'm going to compare 1000H address with something. Before that, I go to instruction set and open compare. It can be memory immediate or memory register. So I can use it with memory, for example, immediate. I'm going to check it with C2, if it is C2 or not. This will update the flags. According to those flags, I need to jump into some place. For example, I'm going to use jump equal and jump not equal. These both two statements. I'm going to use jump equal, for example. If they are equal, go to, for example, equal. There should be equal label and not equal label. K-N-E not equal. Okay. Within this equal part, we are going to use this code. Not equal part, we are going to use this code. Okay, after both of these, we are going to return. So let's emulate and see if this is correct or not. This is obviously not correct, but let me show you why it's not correct. Okay, we put some value into 1000H address. It's not important. It's AB. Okay, we are going to compare AB with C2, which is going to be, let me open calculator, programmatic, AB minus C2, which is minus 23. So the result will be minus, sign flag will be set, 0, the flag will not be set because the result is not 0, etc. Let's go over one and see the results. Carry flag is set, sign flag is set, 0 flag is not set. We are going to use 0 flag. Why? Because we choose jump equal and jump not equal. These two instructions both look at the 0 flag. Okay, jump equal and jump not equal, both of them looks at the 0 flag. So I'm using 0 flag. So is this gonna jump? AB minus C2 is not 0. 0 flag is not set. Jump equal. If they are equal, which means the result is 0, 0 flag is set, then it will jump. But it is not going to jump and go over to the next instruction, which is another jump. It will also look at the flags. As you can see, it didn't jump. It will also look at the flags. If they are not equal, it jumps into not equal part. Okay, so this looks correct. But let's put C2 into 1000H address. So this way, the compare operation will update the 0 flag because C2 minus C2 is 0, 0 flag is set. So this jump will jump into equal part. Yes, this is correct. But after that, all of the assembly code is instructed by one. The next instruction, which is this, will be run. So this is not the case we want. This code should not be run after this code is executed. So that's why after the first part, I'm going to use unconditional jump to end. This is the correct statement. If they are equal, it will update with FF, as we can see, and let's go over and look at the 11 part. It is FF if they are not equal. For example, AB. The result will be AA, as you can see. So this is the correct code, but not a good way to show an if-else. It's complicated. There are 2 blocks and 1 unconditional jump, 2 conditional jumps. We should simplify this usage. That's why we are going to do one of these directly. Remember, within this if-else condition, one of these blocks must run. Either this or this will execute it. So that's why I'm going to copy one of them, for example, this one. Before everything, I directly put FF into 1100, and after that, make compare operation. After this compare operation, I'm going to use only single conditional jump. If they are equal, it's already updated. We have nothing to do. Jump to end. If they are not equal, it needs to jump to not equal and work this way. Let's check if this is true or not. AB and C2 are not equal. If they are not equal, it should store AA value in it. We put FF now, but we should expect it to update it. Let's open the flags also. 0 flag is 0, which means it will jump. As you can see, it jumps to not equal part and it is done. So this is correct. Let's put C2 and check if this is also correct. C2, we put directly FF. It compares C2 with C2. The result is 0. 0 flag is set, and it is going to jump. It is not going to jump. And there is an unconditional jump because we should not execute this line. We move over that line, and the result is AA. The result is FF, not AA, because we jump over them. They are same. If they are same, we put FF. Okay. We simplified this a little. There are some other ways also. For example, let's put AA here, FF in here. Remove this unconditional jump and jump into end. For example, check this one. C2 is equal to C2. If they are equal, we put FF. We write not equal, but no need to use label there. If they are equal, we put FF. So in this case, they are equal. So we should put FF. Now we put AA. And I'm going to open the flags. Jump not equal to will not jump because 0 flag is set to 1. It didn't jump and put FF, which is the correct way. So this is true. Let's check with AB. AB is not equal to C2. That's why we put AA first. Checks the compare them. AB minus C2, which is not 0. 0 flag is not set. That's why it will jump to end. So that's it. with a single jump, with a single conditional jump, we cover the topic. Okay, any question? Any question about this code? Okay, there is no question about this. Let's go over and look at the second question. Second question is a bit complicated for you. It says that, let's say some values are in the memory. I'm going to copy this part directly into here. Oops, there's no red. It's just stating that the memory is full of some values. We don't know how many elements are there. We only know that the last element is 0. How do we use this? For example, we have an array and we don't know the size of this array. We only know that the last element is 0. For example, files. We don't know the size of the file. We are going to read the file. We keep looking for the end of file character. If end of file character is came, we shut down the file. That's it. So for those cases, we have to use a loop, which is, for example, endless loop. This is endless loop, remember. Within this endless loop, we will cover what it wants. For example, what it wants, copy this array memory beginning from 2000 memory address. And we just copy the memory into 2000 H address. For example, we are gathering the value from 1000 H address put this value into 2000 H address. But there is a catch. If it is 0, we should stop executing. After this copy operation, we need to check if the AL is 0 or not. If it is 0, we should end. If it is not 0, we should not end. So jump equal means AL is equal to 0, so that it should be jump not equal to. They should not be equal. If they are equal, the program will finish. If they are not equal, it jumps into this label and continues like that. But this keeps using the same memory location. That's why I'm going to use source index as 1000H and destination index as 2000H. This is source index. This is destination index. To these operations, we have to increment source index, increment destination index by 1. By 1 because it says with an ending byte value. These are all byte values. That's why we only increment 1. And this is the correct code. I'm going to explain this byte PTR later. Please be patient. Okay, let's say memory is full of some value and the actual code is here. We use source index as a 1000, destination index as a 2000. I'm going to read from source index into AL. It reads 12. So it needs to put it into 2000 H address. I'm going over and look at the 2000 H address, which is 3000 physical address. After that, we increment the source index, destination index by 1. And after that, I'm going to check if the copied element is 0 or not. I'm opening flex. AL is 12. 12 minus 0 is not 0. So it jumps. Jump not equal means If they are not equal, it jumps. So zero flag is 0, it will jump into Abbas. So this time it will copy the 1001 address, which is 34, copy it into 2000, increment them, and again check it. Some values goes like this, until a 0. 0, 0 is came, 0, 0 is came into AL. Now this compare operation will set to 0 flag to 1, as you can see. 0 flag is set 1, which means didn't jump, and the program is finished. When we go to 2000 H address, the values we have already put into memory is copied into 3000 physical address. Okay. Any question about this example? Question about question is meaningless. Any question? No question. By the way, let me check people are here. Yeah. So byte PTR. What is this byte PTR thing? Within our operations, remember we use AX and put some value in it. Remember, we use, for example, CL, put some value in it, or 1000 H address and put some value in it. Within this example, I'm going to emulate this code, and I want you to see the machine understand part. Let me show you this. I put only 73, but the machine state that it is 0073. I put only 12, it gets 12. There is always a 0, just never mind this most significant 0. It understands the size from operands. If one operand states a size, it copies that much of a value from the memory or value. For example, AX is 16-bit value. It gets 16-bit from second operand. Second operand is not 16-bit, so it creates a 16-bit value, etc. For example, CL. CL is 8-bit. 8-bit, and the 8-bit will be copied from the operand. This operand is already 8-bit, so it didn't put any 0 beforehand. Okay, but in the third line, we copy 11H into 1000H memory address. This line. Any of these operands not state any size. For example, 11H can be 0011H. So it immediate values doesn't state a size. 1000H address, this is just a pointer to an address, so it doesn't show a size. That's why we use byte PTR or word PTR. For example, let me use word PTR in here. Word PTR. By using word PTR, please see the change. We only put 11 in here, but this time there are zeros. Never mind the first 0. It takes 16-bit and put it into 1000H address, starting from 1000H address. It will also use 1001. Okay, that's why we state the size with word PTR or byte PTR or W or B. These are all same things. Okay, as you can also see, these are W and B's converted directly. B's are for byte, W are for word. Okay, this is stating the size. if you use, for example, 8-bit address, it copies 8-bit from it. If you use, for example, AB, it will give an error. It says that 12 AB cannot fit into CL. It's wrong. Yep, this is the topic I need to cover. Okay, byte PTR is dead. And also I'm going to show you some another information, which is equal operand. Equal operand is creating a constant value. Constant means, remember from C, sabit sayılar, constant value. Remember constant. Within assembly, we have constant values also. For example, I'm going to define a constant value with echo. Do you see the color change? I can barely see, but it updates the color of echo. And you can put directly a value into this keyword. 1000 is now a constant. Okay? So I'm going to use constant within these addresses. For example, I'm going to use 1000 in here and use source index in here, get rid of this destination index. So 1000 is 1000, source index is 1000, total is 2000. This is exactly the same code. Let me show you the line of here. It adds plus 1000H address. As you can see, it resolves this 1000 into value, constant value, and use it. Okay. Now go over and look at the third example. Is there any question, by the way, about these topics? Constant numbers, byte PTR, word PTR. Okay. I'm going over to third question. Third question saying that write the memory address between 1500 and 15 FFH. The range is predefined. Hex values that begin from 0 and increase them by 1 to FF if corresponding memory bytes value is equal to 0. The key point is here, if corresponding memory bytes value is equal to 0. Let me delete this code. It states that there are values between this range. Memory is empty, which means 0. Copy value from 0. Okay, that's why I need a loop. I create loop. This time the number of loop iteration is constant. How many times should I run this iteration? An idea? How many times should I run this iteration? Ahmet says 99. Another guess? So actually, this should be FF minus 0, 0. What will be the result? The result will be FF. Or, and the result is FF, but it can also be 1000H. These are all H, remember. FF plus 1 is 1000H. So we run this iteration 100H or FFH. It's not that important, just don't be over far away. For example, 99 is wrong. For example, 99H is acceptable, but 99 is wrong, Ahmet. Okay, we have a loop. Question say that if the memory is empty, put some value in it. The value is starting from 0. I'm going to use BL or BX. I'm going to use BX starting from 0. I need to check if the value within 1500 H is equal to 0 or not. If they are equal, which means memory is empty, we need to copy this BX into 15 FFH. Sorry, 1500 hash. And let's use indexes. For example, source index, which is 15 hash. Let's use source index in here, source index in here. If they are not equal, we need to end this loop. I'm going to use not equal. If they are not equal, to end. And after this loop, we have to end label. Okay, it checks if the location is 0. It didn't jump and move into here. And after this operation, we need to increment BX and source index also. This is our loop. Run 100 times. Let's emulate this code. Open the Flex, by the way. Okay, we put 100H, which is 100H, as you can see. 1 in CH, 00 in CL. Okay, BX is 0, nothing to change. Source index is 1500. And we are comparing source index value, which is, let's go over and look at the value, which is 0. 0 minus 0, which will be 0. So 0 flag is set. Just because 0 flag is set, this jump will not jump. Because if they are not equal, it will jump. If they are equal, it will not jump. So that's going to instruct the next instruction, which is copying BX value, which is currently 0, into source index. Okay, increment BX, increment SI, loop, CX is decreased by 1. This will run several times. Let's run this several times. Okay, stop it in here and go over and look at the 1500. As you can see, we keep putting BX value in memory. Let's put some value in this range so that the program finish at that location. For example, I'm going to use 73 in the 1505 memory location. This program run 5 times and should end, but it didn't end. There is something wrong with this code. Okay. What is there? We put 15, we put 73 in the in the 5005 address. Let's go over and look at the address 1505. It puts 73 in the byte value. Compare operation is byte value of source index. Source index is 15. 15 address, it will compare with 0, and flags are here. 0 flag is set, so it not jump. Put bx into source index. Oh, that's why we use bx. We should use bl. It keeps looking for word, and that's why it is keep running. This should finish. Yeah, it runs 5 times, and when it comes to 1505, the physical address of 2505, 73 is there, so the memory is not empty, the program is halted. When we put bx in here, for example, let's write bx in here again and emulate. You can see the code in here. It gets the word from bx, which is 00 something, and look at the value of left. Left address is just a byte value, comparing it with a word value. Sorry, not that line. This line. Sorry. Let me reload this one. This is wrong. Why wrong? Bx is increased at some point. Seven, 9, A, B, C. It goes like that. Why this is wrong? It deletes the 73, overwrite it. For example, in here, we have 73 in here. When we goes to 3, 2, 4. In here, 73 is here, 4 is here. 4 is written, but 5 is also updated because we copy bx. Bx is 16-bit. The upper part of bx is 00. We overwrite the bx. We overwrite this 5 value so that it will always become 0. So be careful about the sizes you are using. Okay, this is the third question. Let's open the answers if there is any other different thing. Third question. Yep. Let me copy this code. Down this line. Setting data segment. Don't forget this setting. Oh, it used bx in here. Less register. Yeah, but it's not using compare operation, so this is actually wrong. I need to update this code. Okay, that's it. The question is not clear. Either it's continue or halt the program if the memory is not empty. The question is not clear, so there are multiple answers to this question. I'm going to publish this version, and the video that we recorded in this session is in the recorded part. You can see both answers by this way. Any question? Any question about anything? Sorusu olan var mı arkadaşlar? nested loop yapabilirsiniz arkadaşlar. Dediğim gibi bunlar sadece jump, yani şöyle ya da kaydetmeyeyim.
Abbas hocam elinize sağlık. Teşekkür ederim. Arkadaşlar katılımınız için teşekkür ederim. Benimle ilgili bir soru var mı?
Bana bir soru sordular hocam. Siz kaydı durdurun. Ben o
Teşekkür
soruyu
ederim
uzun uzun
hocam.
açıklamaya
Dilinize sağlık. İyi
Sağ
akşamlar
olun.
diliyorum. Hoşça kalın. Hoşça kalın. İyi akşamlar.